In the previous lectures, we've seen that we would like to have current sources with very high impedances and that cascodes provide these. However, they come at the expense of voltage headroom, and we would like to have both a high voltage headroom and a high impedance from our current source. Now, if we were to do a KVL loop from ground to the top of the lower transistor in the cascode at the output, we would get the following loop. We would need a VOV plus a VTH for this transistor, a VOV plus a VTH for this transistor, and a VOV plus VTH for the upper transistor in the output cascode. And in order to achieve our desired result, which would be to just have one VOV across each of the output transistors, we would need to add an extra VTH into this KVL loop. Of course, it's very difficult to achieve a floating voltage source or a battery in an integrated circuit process, and so our solution is going to be to add another path, another current path. So here we have transistors M1 through M6, and we're going to set M1, 2, 3, 5, and 6 to be equal, and we're going to set M4 to be a little bit different. So if we look at the same analysis, what we want is a VOV plus a VTH across M3. We want 2 VOV plus VTH across M4, a VOV plus a VTH across M6, and finally we'll get one more VOV plus VTH across M2. And if we do this, we would only need one VOV across each of the output transistors in the cascode. And we would solve the following KVL loop to get to that bottom transistor in the cascode stack. Okay, so the secret sauce here is that we want to achieve twice the overdrive voltage for transistor M4 of any of the other transistors. So the overdrive voltage of transistor M4 is equal to the square root of 2 times its drain current divided by mu n C aux times W over L. 4. If we want this to be twice the overdrive voltage of all the other transistors, we simply need to multiply this by 2 and if we solve this out, we would show that W over L4 is equal to 1/4 of the W over L of all the other transistors. So the question is, what does it cost to achieve this higher output swing? Well, we have one extra path that needs to be biased, so this does cost more current. We say this often with analog circuits, but there's always a trade-off in achieving a desired goal. If we want higher output swing, in this case we're going to burn more current to achieve that higher output swing. Okay, that will be it for our lessons on current sources, and in the next class we'll start looking at ideal voltage amplifiers.